Welcome in Dark Core. If you've ever wondered what's at the end of the universe, you're not alone. Great physicists such as the late Stephen Hawking and many other theoretical scientists have been pondering this question for decades. However, the answer to that is not so simple. We have some ideas of what might be past the so-called end of the universe, that boundary which everything in the observable universe slips past, never to be seen again. In fact, even our own galaxy and the billions of galaxies we can see are traveling towards this edge of the universe. And recently, it was found that the universe is accelerating, pulled on by some unseen and mysterious force. Many of you might be asking, what is an event horizon? To put it in simple terms, it is a well-defined surface or edge, and within the inside edge nothing can be seen. It is a notional boundary beyond which no light or other radiation can escape. It is a point of no return. But to get an idea of what might be at the end of the universe, we need to start with how the universe began. Before the beginning of the universe and time, there was thought to exist an initial singularity that had infinite density and heat. It was thought to have contained all of the mass and space-time of the universe. Quantum fluctuations caused it to rapidly expand, and the subsequent inflation created the present-day universe. This is called the Big Bang Theory. This idea began with George Lemaitre, who first noted in 1927 that an expanding universe could be traced back in time to an originating single point. And since then, scientists have built on his idea of cosmic expansion. Looking out at distant galaxies, it was discovered that the farther away these galaxies were, the faster they seemed to be moving away from us. It would make sense that if things in the universe are growing farther apart as time goes on, they must have been closer together at one point. This universally accepted theory is said to have occurred some 13.8 billion years ago. Over this time, space itself has expanded, matter has undergone gravitational attraction, and the result of the Big Bang is everything that we see today. But as vast as the universe is, there's a limit to what we can actually see. Beyond a certain distance, past the particle horizon and the event horizon, galaxies disappear, stars start to dim and fade out, and no signals from the distant universe can be seen. There is no evidence that the universe has an edge, but that doesn't mean one doesn't exist. From our perspective, it looks like we're at the center of everything and every single galaxy is flying away from us. So that naturally leads to there's got to be an edge line of reasoning. But here's where things get interesting. Let's say we hopped over to the Andromeda Galaxy, which is our nearest galactic neighbor. If we lived in Andromeda, everything would look the same, as if we were at the center of the universe and everything was flying away from us. Even if we teleported to the most distant galaxies that we can see in the observable universe, it would still seem as though we were at the center of the galaxy and every other galaxy, including the Milky Way, will be racing away from us. Beyond our own galaxy, there's a sea of around 2 trillion galaxies in total in the observable universe. The stars and galaxies out there look very much like our own, but as we look farther away, we see the universe as it was in the distant past, which are less structured, hotter, younger, and less evolved. All those galaxies come in many different types, shapes, sizes, and masses. But as you start to look back at the more distant ones, we start to find something unusual. The farther away a galaxy is, the more likely it is that it's smaller and has less mass. The stars in these galaxies are intrinsically blue in color than the nearby ones. These smaller, blue, and younger galaxies evolved at earlier times. For a galaxy that's relatively close to our own, we can say that it's about the same age as us. But look at a galaxy that's billions of light years away from Earth, and you're seeing the light that has traveled billions of years to reach our eyes. In other words, a galaxy whose light takes 13 billion years to reach us must be less than 1 billion years old. That means the farther away we look, we're basically looking back in time. It's simply mind-boggling when you look at the greatest image ever released of the distant universe, which was taken by the Hubble Extreme Deep Field. There are thousands of galaxies in the image, and while all those floating galaxies look close to one another, there are huge distances between each other. Here's some 3D fly-through video. However, what you can't see in simple color is that each galaxy has a spectrum associated with it, where clouds of gas absorb light at very particular wavelengths, which are based on the simple physics of the atom. So as the universe expands, the wavelength stretches. The galaxies that are very distant appear redder than they otherwise would. Using these physics allows us to calculate their distance. And when distances are assigned to them, the farthest galaxies are the youngest and smallest ones. Beyond these galaxies, you would expect to find the first stars, and then nothing but neutral gas. This would be during a time when the universe didn't have enough time to pull matter into a dense enough form that would create the first stars. Going back millions of years before this, there existed radiation in the universe that was so hot that neutral atoms couldn't form, and photons would simply bounce off charged particles continuously. When neutral atoms did form, that light streamed in a straight line and left behind a glow called the cosmic microwave background, which is thought to be leftover radiation or heat from the Big Bang. This relic radiation permeates the whole universe in all directions. It is the oldest electromagnetic radiation in the universe. This CMB provides some insight into the composition of the universe as a whole. Most of the universe is made up of dark energy. It is a mysterious force but is driving the accelerating expansion of the universe. The next biggest element is dark matter, which only interacts with the rest of the universe through its gravity. Dark matter isn't something that can be seen, but it is a hypothetical form of matter which is thought to account for a large chunk of matter in the universe. There is a lot of debate around whether dark flow is real and what could cause it. There is one idea that some mass that existed very early in the universe, before cosmic inflation when the universe was extremely compressed, made such a big impact on the matter of our universe that some galaxy clusters are still drawn to it to this day. It has also been recently found that this acceleration of the universe is increasing, with dark energy pulling on everything. This discovery was made in the 1990s and was a surprise to astronomers because everyone believed that everything in the universe was slowing down. Scientists argue that there must be some sort of mysterious force, this dark energy, pulling the universe apart. The fabric of space wasn't just expanding, but the expansion was accelerating. What we do know is that if the universe weren't expanding, gravitation would cause everything to collapse down to a single point. The fact that the universe hasn't done that allows us to conclude that something has prevented that collapse. Either something counteracts gravity or the universe is expanding. The edge of the observable universe is called the particle horizon and lies roughly 47 billion light-years away. It is always receding, both because the universe expands and because light from increasingly large distances eventually reaches us. The cosmic horizon is roughly 42 billion light-years away. This is the current distance beyond which light emitted at this cosmological time will never have a chance to reach us. The options for what lies on the other side of this cosmic horizon, or end of the universe, are as infinite and sometimes improbable seeming as a very human imagination that ponders it. The accelerating expansion of space means that the space between us and faraway galaxies expands faster than light can travel through space. Therefore, there could be many other galaxies and worlds beyond this. Scientists cannot agree yet on what the basic shape of the universe is. Some believe it is an easily imagined sphere, a sort of gigantic marble of life and energy. Others think the universe must be shaped inversely, in a negatively curved satellite shape. Others believe it is flatly dish-shaped, a sort of infinite plate of sky. Therefore, the question isn't so much what lies at the end of the universe, but if the universe has an end at all. If you were to look at a map of our observable universe, it might look something like this. Although this defines our observable universe, including the theoretical boundary of the Big Bang, this is not a real boundary in space. It is simply a boundary of time. That is because there's a limit to what we can see because the speed of light allows information to only travel so far over 13.8 billion years since the hot Big Bang. But what would we see if we somehow went to just a tiny fraction of a second earlier than when the universe was at its highest energies, hot and dense and full of matter, antimatter, and radiation? We would likely see cosmic inflation, where the universe was expanding ultra-fast. However, inflation has an intriguing consequence for the ultimate fate of the universe. There have been theories on the ultimate end of the universe. If the universe continues to expand indefinitely, the result would be called the Big Freeze, where the entire universe approaches absolute zero temperature. Eventually, the supply of gas needed for star formation will be exhausted, and as existing stars run out of fuel and cease to shine, the universe will slowly and inexorably grow darker. Black holes will dominate the universe, which themselves will disappear over time as they emit Hawking radiation. Or it's possible that the universe could collapse on itself, a sort of reverse Big Bang. Of course, there is no reason to worry about any of these events, as they are trillions of years in the future. But one thing is certain. We live in an exciting age where more and more things will be explained, such as dark energy and dark matter. These may be the keys to unlocking the greatest mysteries in the universe. We hope you enjoyed this video. Do you think that there's anything out there past the cosmological event horizon line waiting to surprise us? Tell us what you think in the comments. If you liked the video, then click the big red subscribe button and turn on notifications so you'll be the first to know when we release a new video. We want to thank you for watching Dark Core, and we'll see you next time.